Hi guys, today we're going to be talking about weight and balance and why that's super important to us as pilots and why we should respect the limitations of the aircraft. So in class I had a video to show. Let's see here in the clip you can kind of see this larger airplane. I believe it was a 747. It's sort of an unusual attitude there, something that you don't really see happening or you shouldn't see happening. And what we discussed in class was the fact that this was a cargo plane, right? It was operating in, I think, Pakistan or somewhere in the Middle East, and the aircraft was loaded, and all of the pallets and everything were strapped down in their respective places. But after takeoff, I guess something failed. One of the securing straps or something failed, and the pallets moved back. And what that did was it changed the concentration of weight or the center of gravity, moved it too far back, right to the point where the pilots couldn't have adequate control of the airplane, right? So they end up entering kind of a spin, right, the beginning of a spin, and they're just way too low to try to recover, right? So unfortunately, this ended in fatalities. But that kind of illustrates why weight and balance is important. And in the case of that airplane, they did everything they were supposed to do except for, I guess, secure the load properly, or maybe they didn't check the integrity of the straps or the lock system. But yeah, unfortunately, that's what happened there. Right. So when we talked about aerodynamics, we did talk about weight. We didn't really spend too much time on it because weight has always been something that's kind of self-explanatory, right? Everything that has mass has weight, right? And it's a downward force that gravity causes to happen, right? So the reason why we're not just floating off the ground is because we have weight, right? Okay. Now, in the case of the airplane, remember we talked about how sometimes other downward forces could be combined with weight to work against lift. Well, that's something that kind of becomes relevant here, that we will kind of revisit, right? And we talked about load factor as well, right? So anytime we have a weight, load factor serves as a multiplier to whatever that weight is. So the greater the weight we have, right, and the greater the load factor, then the greater the weight that the airplane feels like it's needing to support. Okay. Now, if we are to successfully take off and climb away from our starting altitude, right, at an airport, then we know that lift has to momentarily be greater than weight, right, to allow the aircraft to leave the ground. And then once we're kind of situated in that new climb attitude, then the forces kind of balance out again, right? We're not accelerating our rate of climb or, descent if that's what we were doing. It's regulated. So if we have too much weight to the point where we can't really make that momentary um, imbalance happen to where we can leave the ground, we're going to have problems, right? Even if we do leave the ground, right, we might notice some interesting things, right? We might have a longer takeoff roll. We might notice that the climb performance is not really that great, and we might notice how much harder it is to kind of pull that nose off the ground, right? We might have to add a lot more back pressure just to leave the ground. So part of that, or I guess most of that, comes from how much weight we have on board, but some of that can also come from the balance aspect as well, right? Um, so make sure that when you are going on cross country or even a local flight, right? Let's make sure that we observe the limitations that the manufacturer has posted in the POH. So make sure you're under that maximum. Excuse me. Make sure you're under that maximum takeoff weight. And for the balance portion, make sure that your CG is within limits, right? When I say CG, I mean center of gravity, right? And we kind of talk about this loosely in everyday life. If we have trouble with balance, we might talk about our CG being out of whack. My wife is 32 weeks pregnant right now. She's had to kind of figure out where her CG is, right? It's a little bit further out in front than she was used to. Um, so that's something that's important to airplanes too, right? In the case of that 747 and that video that I just talked about, the issue there was the fact that all the weight moved back. It wasn't that there was additional weight added or they left the ground with too much weight to begin with, but it was more so the fact that that center of gravity moved back because the concentration of weight um, well, a large part of it anyway was in the cargo pallets that shifted backwards. Okay, so there is a prescribed limit in the POH for CG location, right? And we'll talk about like what this means, like where is my CG? Um, but center of gravity itself is, by definition, right, the place where the weight of the aircraft is concentrated. So it's a fixed point. And then if you change the weight or the location of these items that are in the airplane, then you will have a change in CG. And we can't really go out to the airplane and do this, but for illustration purposes, imaginative illustration purposes, if you calculated the CG of the airplane and you put a hook in the ceiling of the CG, right? You drilled it in, and you got a rope, and you had a hoist team or a crane or something, and you guys lifted up that airplane, right, on that rope and on that hook. Then what would happen is there would be no tipping forward or backwards. The airplane would be completely balanced if it were suspended. Okay. So when we have the CG in different locations, we can expect a few different handling characteristics and behaviors. And some of these are good, some of these are bad. Every location has pros and cons, okay? But when we talk about CG limits, right? When we say forward limit, that means that obviously it's a little closer to the nose of the aircraft, right? And this is typically a lower number, okay? So lower and forward are pretty much the same thing. And then if we say we have an aft CG, right, we don't say we have like a far back CG or, I don't know, a backward CG or something. We say we have an aft CG, okay? And that's going to yield a higher number for CG location. And yes, we'll characterize that as aft. So working beyond that, let's just like go through some terms and definitions that will probably be really helpful in understanding all this. So basic empty weight is a great place to start. Basic empty weight is essentially the plane without anything else. Okay, so you've got the airplane, you've got all the standard equipment in there and everything. You've also got unusable fuel and undrainable oil, right? So fluids you can't really easily take out. Hydraulic fluid counts too, right? So all of the stuff that is a part of the airplane and all undrainable fluids is your basic empty weight. So when you go to calculate your weight and balance, this is like your starting point. You would go on our RMS website, right? And then you could find, or you could do it in Talon too, but in either location, you'll be able to find a list of basic empty weights for all of our airplanes, and they give you a little bit more information with it, but the basic empty weight is probably the most important part. Okay, so you've got that. Maximum ramp weight is essentially just how much can this airplane weigh on the ground. Okay, and sometimes your maximum ramp weight and your maximum takeoff weight are the same thing. But in the case of the Cessna 172, the manufacturer gives us a slightly higher maximum ramp weight, so we can have just a little bit of extra fuel. So it's a 7-pound difference. And if you remember from the performance charts, remember that note on the climb chart that says allow for a burn of 1.1 gallons for startup, taxi, and all that stuff? Well, that's what they're getting at there. So the ramp weight is slightly higher because they're allowing you to have a little bit of extra fuel to account for that 1.1 gallon burn. And then that brings us to our maximum takeoff weight, right? So that's just the maximum weight that we can legally be at for takeoff. Um, if you overloaded the airplane by 50, 100 pounds, you would still leave the ground. However, that is not legal, right? And I wouldn't really want to try it. We find ourselves close to the limits when we have things like American Airlines Day or United Airlines Day. We have all these prospective students come down and tour the facilities and fly with us. So when we actually fly them around kind of the area, so they have a little taste of what it's like. There are 3 of them in the airplane. There's one of us instructors, and then we've got like half tanks of fuel. I think even less. I think the last time we did it, we had 10 gallons in each. I think so. I think that sounds right. 10 gallons in each. So, I mean, we really weren't able to take that much fuel, but on the takeoff compared to normal everyday operations when it's just a flight instructor and a student, and we've got maybe half tanks. It was a noticeable difference, right? It was a little harder to climb out, had to have a little less of a high pitch attitude to kind of yield that VY airspeed we were looking for, so our climb performance wasn't as great. Um, so yeah, sorry, I'm going off on a tangent. But anyway, useful load is basically how much can you put in the airplane, right? So you've got your basic empty weight, and if you subtract that from your maximum takeoff weight, that is essentially your useful load. So how much more weight can I put in this airplane until I reach my maximum takeoff weight is essentially what that is. So the actual oil that goes in is usually counted as part of the useful load, like whatever is drainable, right? Of course, the people that get in there, the fuel. If you have bags or cargo or anything like that, that's going to count for useful load. Some people, if you're doing, let's say, a skydiving operation, you would want an airplane with a pretty decent useful load, right? Because your goal is to get as many people up to altitude as quickly as possible so that you can descend down, grab the next group of people and do the same thing, right? So that might be something you were looking for if you're running an operation of that sort. Okay, the datum is just pretty much an arbitrary line, right, or plane that they stick somewhere on the airplane to measure the distance of, I guess, items from, right, the locations of different aircraft parts. So you can see here in the picture, the datum is between the cowling and the cabin, right? So for the Cessna airplanes, the datum is the firewall there between the two, and everything out in front of the datum, so everything in the cowling all the way out to the propeller, is negative in terms of distance, right? Because the datum is like 0. Okay, so if we measure, let's say, the location of the propeller, then our distance we would have to make negative because it's out in front. Okay, but if we go aft of the datum, then everything in that direction is positive, right? So that's where we get into arms as well. Arm is literally just how far from the datum something is. Okay, so if I'm measuring the arm for, I don't know, the fuel tanks in our airplanes, for the most part, that's about 48 inches aft of the datum, so that's going to be a positive value. If you look at the little 10-pound weight here in the picture, that has an arm of 70 inches, right? And because it's aft of the datum, it is it has an arm of 70 inches. Okay, so we measure the arms in inches as well. Station is kind of the same thing as arm. You might see it in the POH that particular items are at certain stations. All that means is it has an arm of the same magnitude. So like for that 10-pound weight there, you can see it has an arm of 70 inches, but it also sits at station 70, right? And it calls the datum station 0. So that's all that's saying, okay? So those are kind of the same thing. You might see one or the other. And then moment is kind of the culmination of all this, right? So when we measure the arm of a particular item, we consider both the distance from the datum and the weight of the item, right? And when we multiply those two things together, we get the moment, which is a torque rotational force, right? So that's basically how, I guess, how strong is the rotational force that that item provides, right? So the longer the arm, right, the greater the weight, the greater the rotational force is. If you think about your place in an airplane, if you sit up front, right, when you're doing turns, you don't really feel much of that, and that's because you have a shorter arm from the like the center of gravity that you're pivoting around, right? When you're doing the turns and stuff. But when you move back, if you're sitting back seat and you're observing a flight or something like that, you will feel like you are traveling a lot farther. And that is true. That's because you are sitting farther back. You've got a greater arm from that pivot point. Okay. So you, in essence, have a greater moment. So that's why you kind of feel that more. Same thing if you sat in the back of a bus as a kid, right? The pivot point in the bus was somewhere between the front and the back tires, but if you were all the way in the back, then you got an extra long arm, right? And if that bus driver was making some like wild turns, right, really fast, you were kind of getting thrown all over the place. Okay, so that's where that comes into play. So moment is arm times weight. So in this example, you can see the arm or the station of that 10-pound object is 70, right? And the weight of the object is 10 pounds, okay? So if we do 70 times 10, that gives us a moment of 700 inch-pounds, okay? If we were measuring something out front, then that moment would be negative, right? So it would be whatever that negative arm is times the weight, and that would give us a negative moment, okay? So the best way to kind of start with weight and balance is just kind of using a lever, or if you really want to picture it as such, a seesaw, okay? So if we want this lever to balance on this fulcrum, right, which is kind of that point on which it rests, we have to have equal moments on either side of the fulcrum, okay? And the other thing to notice is in this particular instance, the datum is at the same place as the fulcrum, right? So we follow the same rule from before. Everything left of the datum is negative, right, when it comes to the arms or the stations. And then everything is positive on the right side when it comes to the arms of the stations, okay? So this might be a better illustration of what a moment kind of is, right? So um, if there was an imbalance in moments between these two sides of the seesaw, the lever, then it would rotate the seesaw or lever in that particular direction, right? You can see the lines here. You can see the positive forces seek to rotate it in a clockwise manner, right? And the negative forces seek to rotate the lever in a counterclockwise manner. Okay, so if we want there to be balance, then both of those forces that are seeking to rotate the seesaw in those opposing directions, they have to be equal. Okay, so how do we do that? Well, it's all about that math, right? Weight times arm equals moment. Okay, so if we look at the example here, let's start with the left side, right? We've got a 100-pound weight, and it is at a location of negative 50 inches, right? So that means it is forward of the fulcrum, so that's why it's a negative value. If we want the moment from that, we just need to multiply the arm times the weight. So we multiply the negative 50 times the 100, and that gives us negative 5,000. Okay? Now, if we want the moments on both sides to be equal and cancel out, then we need something that gives us 0, right? So if we have negative 5,000 on the other side, then we need to add 5,000 to that to get 0. So what that tells us is on the other side, we need a moment of 5,000. Okay, so if we've got a 200-pound weight, we need to figure out where to put it, right? And if our math, I'm going to start writing here. If our math is, here we go, here's my pen. If our math is weight times arm equals our moment, then we can use that to figure out how we're going to get that 5,000, right? So, oh, that was not good. Let's try this. Okay. Okay, so we know we have 5,000 for the moment. And we know that the weight is 200 pounds. Okay, but now we need to solve for the arm. Another way of writing multiplication or implying that multiplication is supposed to happen is writing variables and values next to each other. So that's all I did here is 200A is equal to 5,000. If we divide both sides by 200, I do apologize for my writing. It's not good using a mouse. These zeros cancel, okay? And now we have 50 divided by 2. So our arm equals 25, okay? So you can see here, right, that's what it says, is our weight is 200 pounds on that side and our arm is 25 inches, right? Or it's sitting at a station of 20, or at station 25 is where it's sitting. Okay, and you can see, right, both cancel, okay? So we have a moment of 0 between the two. So we have balance. If you had to figure it out the other way, you could, right? If we didn't know, let's say, the weight of object B, but we knew that it had to have an arm of 25, right? Because that's the only place we could put it, then we could run the math the same way, except in this case, we would have the arm, right? So we would have A, and we would be solving for W. So that would just be the right, it'd be 25W is equal to 5,000, right? Divide both sides by 25, and then that would give you 200. So whatever way you need to swing it, whatever information is missing, you can make it work, okay? And if we need to change a moment, right? Let's say we didn't have a perfect balance, then we could change either of those variables. We could increase or decrease the weight depending on what we needed, or we can move the arm, right? We can move stuff forward, or we can move stuff back to get that balance, okay? Okay, so if we move on to some practice here, we can look at a few different things, right? We can have a few different examples to kind of practice this, right? So if we've got a 20-pound weight with an arm of -5 inches on one side of the fulcrum, so this would have to be the left side, right? Because only negative values go on the left side or forward of the datum. And we've got a 50-pound weight on the other side. Well, how long does the arm have to be? Okay. So we know we've got, let's see, let's just go ahead and just do this whole, okay? So we have 200, or I'm sorry, 200, 20, right? 20 pounds. And we want our moment, right? So 20 times the -5 is weight times arm. Okay, and that gets us a moment of -100. Okay, if we're trying to figure out where the 50-pound weight on the other side has to be, then we can set that equal to this. Okay, so we have 50, and then let's call it, let's do A. I was going to do X by default, but let's do A. Okay, because we're trying to figure out the arm. So 50 for the weight, divide this, and then we should have 20. So I kind of skipped a little bit of a step there, or not 20, sorry, I can't math. 2. 2. Okay, I kind of skipped a step there too. What I didn't do is I didn't take away this negative here for the 100, right? We know if the moment on one side is supposed to be -100, then the moment on the other side should be 100 to cancel both out. So that's how that should be. You know what? I should have just let my slide do all the math for us because I totally forgot I had all this, right? So there's our moment on the left side like we talked about with proper math, right? So we need to generate a rotational force or a moment of 100 inch-pounds on the other side. I have it backwards there, but we need that on the other side, right? So if we remember that arm times the weight equals the moment, then we can rearrange that to solve for the missing arm, right? So it would be moment divided by weight is going to give us our arm. We have the moment that we're supposed to achieve, and we have the weight. We just divide those, and we get a 2-inch arm. Okay. So another way to kind of practice this new thought process is to figure out different combinations of weights and arms that'll give us the same moment. Right? So if we need to generate a 500 inch-pound or pound-inch moment, I honestly don't remember which way it's supposed to be, but if we want 500, right, we can do this a variety of ways. We can have a 1-pound object, 500 inches, right, after the datum. If we multiply the 5 times 100, that gives us a moment of 500. Or we could have a 500-pound weight 1 inch after the datum, right? And we could have anything in between that. We could have a 10-pound weight, right? 50 inches aft. We could have a 50-pound weight, 10 inches aft. There's just a lot of combos, right? So we could have any of these to achieve that moment. Okay, and there's of course other combinations and things, but just to kind of keep everything nice and neat and square and decimal free, that's the extent of the examples I have here. Okay. All right, so if we kind of evolve the thought process, right, if we separate the location of the datum and the fulcrum, then it becomes a little bit different and a little bit interesting, right? So in this picture, I've kind of trimmed it off a little bit to not show the location of the datum, or I'm sorry, the fulcrum, right? But you can kind of see maybe the knob for it. But what we've done is we've moved the datum all the way to the left. Okay, so if the datum is all the way to the left, then everything on the right side is considered after the datum, right? So all of those values will be positive. Okay, there'll be no more negative values, just positive. And what we are trying to now figure out is where to put the datum. We're not concerned about where to put the weights because we already know where they are, okay? And we just need to figure out where to put the fulcrum in order to balance this, right? Where do we need to move that so that this seesaw doesn't tip in either direction, okay? So what we need to do for this, right, and we've already kind of talked about all that, okay? We need to calculate the moments, right? So that's step number one. So let's go ahead and do that. So object A, right, is 100 pounds, and it's 50 inches after the datum. So that's a moment of 5,000. Object B, I'll let you guys take care of that one, right? 100 pounds, 90 aft, 9,000. Okay, and then for object C, right, 200 pounds and 150 inches aft, it's going to be a 30,000 pound moment. Okay, so we figured out the moments for all of these things, and we need to add them together. Okay, now what we are trying to essentially find is the center of gravity. Okay, where is the center of gravity of these different items at these specific locations and weights, so that we can have balance, right? And the fulcrum is a symbolization of that we've been talking about so far. Okay, so the CG is the fulcrum. Okay, now in order for us to find the CG, we have to kind of go off of that. We have to riff off of the original equation, right? The weight times the arm gives us the moment. So far, we've found all of the moments for all the objects. So we need to add those together so we know what the total moment of all this is, right? Looks like just doing some mental math here, it's 44,000, right? Okay, do we have any other information? Do we have the arms? Yeah, we have the arms of the individual items, but do we have the arm location of the fulcrum? No, that's kind of what we're trying to find, right? So that's the missing link right now. Do we have weight? Yeah, we have weights, right? If we add up all the weights of the balls, right, then that gives us our total weight. So we have total moment and total weight. If we add up all these weights, that gives us a weight of 400 for all of that, okay? So if we just kind of go off that equation, right? We have the weights, we have the moments, we're missing the arms. How do we get the arm, right? How do we rearrange this equation so that we can get the arm? Well, we need to divide both sides by weight, right? So in this case, the arm is equal to the moment divided by the weight, okay? So we figured out these totals, right? We have 400 pounds of weight and 44,000 inch pounds for the moment, right? So all we need to do is plug these values into that equation. So if we divide the 44,000 by the 400, we get 110, okay? So what this tells us is that the fulcrum, which is like our CG, needs to be placed 110 inches after the datum to achieve balance. Okay, so that the moments will be equal and that we won't have imbalance. Okay, so the fulcrum will go about right here. Right, you can see how this is 90 aft, right? This is 150 aft, so it's got to go somewhere between here, maybe a little closer to the 90. But that's where it should be placed in order to achieve that. Okay. All right. So that was very basic weight and balance. right? We added up the weights of things, we found the moments by doing a little bit of multiplication, and then we did that division to find the center of gravity. So it's essentially the same thing, we just have a few more things to worry about when we actually do real weight and balance. Something that I want you guys to file away in the back of your minds is that fuel, so 100 low lead fuel specifically, is 6 pounds a gallon. Okay, so don't forget that. That will haunt you for the rest of your flight training, right? 6 pounds a gallon. Okay, now, um, November 547 Echo is one of our model G1000s. It's my favorite one, as a matter of fact. So I've gone ahead and I've pulled the basic empty weight information and the moment information from our sources. And you'll notice I didn't pull a CG for the airplane. I could have pulled a CG for the airplane, right? But the CG location doesn't really matter when we're dealing with the basic empty weight. If we have plans to load up that airplane, then we know that that CG is going to probably change. Okay, so there's not really a point in already having that information if it's just going to change. But the basic empty weight of the airplane is not going to change, and the moment that is generated from that is not going to change either. So in order to incorporate the rest of our things into the weight and balance planning, we have to become familiar with the loading arrangements chart in the POH. So for this, it's just kind of a cutout of an airplane or a top-down view. And you can see we've got pilot passenger stations, we've got rear passenger, we got baggage area, we got baggage area B. So all of these are rough guidelines to where the I guess the objects are, right? So if we're sitting up front, then we should maybe suppose we have a station of like 37 inches after the datum, okay? Or if we're in the back seat, right, it's 73 because that can't move. The range of 34 to 46 just reflects the fact that you can adjust your seat when you're up front. So you might very well not be at 37, but we just kind of use 37 as an average, unless you want to count how many, I guess, clicks back you go and try to figure that out, but I wouldn't waste time doing that. The most helpful note is going to be the fact that the useful fuel CG arm is located at station 48. Okay, so that's also something to remember, station 48 for that. All right, so that's the loading arrangement chart. If we look at the weight and CG limit chart, right, this is what tells us whether we are within the limitations of the aircraft that the manufacturer has published. So you can see, right, the maximum takeoff weight is capped off up here. It doesn't even deal with the maximum ramp weight, right, because we should be shooting to be at the 2450 by the time we take off. So as long as we observe the maximum ramp weight, then we should be down to the 2450 by the time we're cleared for takeoff. So that shouldn't be a factor. We've also got a few different things, right? We've got the utility category and the normal category. Don't worry too much about that right now. The important thing is we are in this area overall. So we're following max weight, and we are also following the forward and aft CG limitations. Okay. All right, so let's do a little bit of planning here. So we're going down to Nashville, if you recognize that code. We're taking full tanks, right? So full fuel and 547 Echo. The instructor flying weighs 160 pounds. The student weighs 195 pounds. If we are taking full tanks, right, then that is 53 usable gallons in the Cessna 172Rs. And remember, it is 6 pounds per gallon of 100 low lead fuel. So 6 times the 53 gives us 318 pounds. We require all flights from SIU to go with full tanks, so you'll get very used to 318 if you take the R model, or if you fly the R model regularly. Okay, so 318 pounds. And for kicks and giggles, I put the flight bags, 15 pounds, right? So this doesn't seem like this much or that much weight so far, right? But the thing that I haven't added is the thing that's going to weigh the most, which is the airplane, okay? So if I add that, then you can see that that makes the weight increase quite a bit. So we've got all those weights to be conscious of. And the first thing I would do if I was doing weight and balance is to just add up all the weights, right? Because if you are overweight and you're wasting time calculating the CG location and all that stuff, you're going to have to go back and replan, right? Some sort of way you're going to have to replan. So always just add up these weights to make sure that you're within those limitations before doing anything else, okay? So we add all that up and we ask ourselves, are we at or under maximum ramp weight, right? Because when it's time to take off, we should be at maximum takeoff weight if we are at maximum ramp weight initially. And the answer is yes, right? If you do the math, add all this up, we should get 2,383.5 pounds, okay? So that's under, right? 2450 is our maximum takeoff weight. 2457 is our maximum ramp weight. So yes, we are under that, okay? Now, the aircraft basic empty weight moment, right, we found was 70,166, right? Okay, now we got to ask ourselves some different questions in order to find the rest of the moments, right? So we've added up the weights. We're now in the process of figuring out the moments to add those up, okay? Because remember, we're trying to solve for that CG location, which is arm, right? So weight times arm equals moment, but arm is what we're missing, okay? But now you have to focus on the moment. So which station would the flight instructor and student sit at? Well, we're going to be sitting up front. And like I said, unless you want to spend time trying to figure out exactly where you are after the datum, then I would suggest just rolling with the 37, right? So I'm going to go ahead and times both the weights of the occupants by 37 to get their moments, right? So 5,920 for the student, or the flight instructor, and then for the student, it's 7,215, okay? Next thing to ask ourselves about is fuel, right? We're bringing full tanks. Where is that located? Well, if we remember to look at the notes, it is station 48. So 318 pounds of fuel, right? And I think that's the mistake I see a lot is people forget to convert gallons to pounds. Do not forget to do that. But 318 pounds times the 48 gives us 15,264 as a moment for the fuel. And then the bags, we could put the bags in a number of places, but more than likely they're going to go in that back seat, right? So that is station 73. So that would be 15 times the 73 gives us a moment of 1,095 for the bags. Okay, so we've already calculated the total the total weight. We've determined that we are under the maximum ramp weight, and now we figured out all the moments, right, for all the things and people. Okay, we are now going to add all of this up. Okay, so when we add the total moment, we get 99,660. Okay, and what do we do next if we're solving for arm that's missing? We go ahead and we divide both sides by weight, right? So arm is essentially equal to moment divided by weight. So we'll do that on the next slide here, and I've got that center of gravity limits chart for our convenience. So there it is, total moment divided by total weight is the aircraft CG, and we divide our 99,660 by our 2,383.5, and that gives us a CG of about 41.8 inches aft of the datum, okay? So if we go in our chart here, we can see that here's 41 inches, right here is 42, okay? 40.8 is somewhere here, and then if we follow that up, we can align that with our weight as well, right? So here's 2350, here's 2400, right? So we're going to be somewhere between there. So if we go to like roughly where all these things meet up and line up, we're going to be about right here. Okay, so we are within the center of gravity limits and the weight limits. Okay, so this airplane is legal in that sense. Okay, category, if you're so inclined, right, is normal. Okay, utility, just to kind of tell you guys, utility is something we use for acrobatics and spins, right? So we want to make sure that the aircraft is going to be able to recover from that state. So we always have a more forward CG for that because we have better stall recovery. So normal, the CG, would you call it more forward or aft? It's kind of in the middle, maybe slightly more forward. I don't know. I don't know. It's kind of smack dab in the middle, but when we have a CG that's a little bit more forward or aft, obviously there's going to be a few different behaviors that we should kind of be aware of, right? So if we think about the longitudinal axis, right, if we revisit this, remember that is the imaginary skewer that runs from the nose straight back to the tail. We've got different forces that act upon that, right? If we're kind of viewing the airplane from the side like we are in this picture. So we've got, again, right, all of those downward forces against all of the upward forces, okay? So the downward forces that act on that longitudinal axis, right, is the weight, right? So the center of gravity is where it's concentrated, and that's somewhere closer to the nose of the aircraft, right? So you can see in the GIF here, it's like moving back and forth, but it's somewhere pretty far out in front, okay? And then for the other downward force, that's all the way in the back of the airplane, right? So we've got the tail down force, and where this comes from is us adding back pressure, right? So if we have to add back pressure to keep that nose from falling or to climb or to do anything like that, what we are really doing is we are not imposing an upward force on the nose of the aircraft, but rather we are imposing a tail down force on, of course, the tail of the aircraft, right? So we are deflecting that elevator surface upward, changing the camber and the wing, causing the airflow to be routed upward, right, while the tail goes down, right? That Newton's third law process, right? So that's what's happening, right? And then consequently, the nose goes up, okay? So the greater the back pressure we have, the greater the tail down force we have. And in the middle there, right, the only upward acting force that we're really concerned about right now in this state is lift itself. So the place where lift is concentrated is, yes, on the wings, right? Of course, that's the purpose of wings, right, as airfoils is to create lift, but there is a spot, and it does move, but there is a particular spot where that lift is concentrated, and we either call that the center of lift or the center of pressure, okay? So that's there, and it's between the two, right? So we've got CG out in front, we've got center of lift kind of in the middle along the wing somewhere, and then in the far back, we've got tail down force, right? So we got these forces acting in different places, and the sum of the downward forces must equal all of the upward forces, right? They have to equal out one another to maintain level flight, okay? So just kind of seeing what's happening with this chart, right? If the CG is moving, then that also affects how much tail down force we have to keep that airplane balanced, right? If we have the CG far out in front, let's say it's like all the way forward to the lowest allowable CG location, then we know that our airplane is inherently going to have a nose down tendency. If we have a nose down tendency, that means this airplane is going to want to descend. We're not going to have an easy time maintaining altitude, and we're going to have to add back pressure, right, to keep that nose up. So if we add back pressure, remember what that does to the tail down force, right? That increases the amount of tail down force that's necessary to keep that nose up. So if we have a further forward CG, then we have to have a greater tail down force. And further forward CG and greater tail down force means that there are more downward forces acting on the airplane, which means that consequently we have to have enough lift to cancel those out. Okay? So that's just kind of the beginning of the thought process there. Okay, so if we compare more forward and more aft CGs against one another, you will find that there are pros and cons to each of these. Forward CG, as I kind of mentioned, has better stall recovery. Okay, it just has that ability to just kind of nose down, right? And if you want to even get into a stall, you have to really make the airplane do it by adding enough back pressure. And then you've got better stability, right? And what I mean by stability is like resistance to motion, okay? If you have a forward CG, right, those are the good things. Here are some bad things. Your airspeed is going to be a little bit slower, and your stall speeds are going to be a little bit higher. Okay, and then as you would expect with the aft CG, the opposite of everything is true, right? You get faster cruise airspeed, you get lower stall speeds, but you do have worse stall recovery with the aft CG and worse stability. Okay, so it's kind of a pick your poison situation, kind of, right? Not really, and I'll talk about why it's a kind of situation. Okay. So if we talk about stability, as I said, it is an object's ability to resist motion, right? So the more stable something is, the harder it is to disturb it from its position. We talked about this before regarding gyroscopes, right? The faster they spin, the more rigidity in space that they exhibit, and the harder they are to disturb from their state, right? So that's why they're able to stay where they're at, and the airplane moves around it, right? And then the instrument gives you the proper indications as a result. So if we look at this gentleman carrying these buckets of water here, do you think that these buckets would be sloshing all over the place more if they were full or empty? I would say empty, right? Because that's less weight in the buckets, right? And if there's less weight, then they're easier to move, okay? You might not be trying to move them, but you might have to do more to kind of stabilize. Whereas if you have heavier buckets, right, the increased weight makes them harder to move, so they have more stability, okay? So if we kind of translate that to the airplane, we can think about one of those buckets, probably the bucket on the left, being that center of gravity, the gentleman actually supporting, right, both of the buckets and everything can be lift, okay? So he's providing an upward force so these buckets don't fall down, right? Because if the force of these buckets is greater than the force that he's supplying to keep them up, then the buckets go down, right? Or our airplane descends, okay? Or if his force is too great, right, then the buckets go up. They don't stay where they're at, okay? So the forward bucket is going to be our CG. He's going to be our center of lift or center of pressure. And then the bucket on the right is going to be our tail down force. Okay. Now you can see here, right, if we have more water or more water in the bucket on the left, or a CG that's, a little heavier, then we're going to need a little bit more tail down force, right? Okay. Same thing happens if we move that bucket, right? So let's say that the stick on the left side went a little farther than that on the right side. That would be equivalent to us moving our CG forward, right? So if you have a further forward CG, then the arm, or the distance between that center of lift and the center of gravity, has increased, right? And anytime we increase the arm or the weight of something, right, then the moment that it generates increases, okay? So the further forward the CG is, the greater the moment is of the CG. Okay, so if we have a moment trying to rotate the airplane in that direction, right, to nose down rotation, then we need to have an equal moment in the back to counter that, right? So we don't have that rotation, so we're stabilized in flight, okay? So if we have a strong force trying to rotate us nose down, then we have to add enough back pressure, right, or enough water to that pail in the back to balance that out, right? And this time, for the tail down force, it's not the arm that's changing, right? The distance between the tail and the center of lift is the same, right? That's not going to change. The thing that's going to change is the amount of tail down force that we are supplying. Okay, so that's essentially the weight that we are increasing, right? So we increase the weight to increase the moment of that force. And once those two things become equivalent, they are that much harder to move, right? And that's equivalent to these pails being full, right? The greater the weights or the moments for both of these things, the harder they are to move. However, if we have a more aft CG, right, the arm between the center of lift and the center of gravity gets smaller, which means the moment is not as strong on that side, so the rotational force is a little bit weaker, which means we don't need as much tail down force on the other side. Okay, so we don't have to remember the arm is not what's changing, but the amount of tail down force, or the weight we are basically imposing on that tail, doesn't have to be as great, right? So if there's not that much weight that we're imposing on the tail, right, to balance things out, then it's going to be a lot easier to move the airplane, right, to disturb it from its original condition, okay? So it's harder for the airplane to resist motion. And the way that I showed you guys this in class was using a pen or a pencil, right? So if I take a pencil, and you can imagine me holding one, right? I've got my thumb in the middle of the pencil, under the pencil, okay? So this represents our center of lift or center of pressure, right? This is that upward force keeping this pen suspended, okay? If I put my pointer finger on the same hand, so I'm using my right hand. If I put my pointer finger on that same hand out in front on top of the pen and push it down to simulate the center of gravity, right? Then you can see, oops, I just dropped my pen, that the tip of the pen wants to drop down, right? So if I want this pen to stay in its original condition, then I need to add my pinky to the back of the pin and provide enough force to keep this pin from moving, right? Okay, if I slide my forefinger or my pointer finger all the way forward, right, and I increase the distance between my thumb and my pointer finger, then the moment on that side increases, okay? Which means that if I want this pen to stay where it's at, I have to impose more of a force via my pinky in the back, right? That's our tail down force, okay? And the greater the force on both sides here, right, because of that increase in arm of the CG, the greater the weight on either side, greater moment, right? So the harder it is for me to actually move this pen, right? I've achieved more stability because of that. But if I move my pointer finger closer to my thumb here, right, that's simulating an aft CG, then I don't have to keep as much force on my pinky to just keep this airplane or pen stabilized, right? But it's a lot easier for me to move it back and forth, okay? So that's a way to illustrate and think about it, okay? Now, if we've got that thought process down, then we can go through the rest of this kind of in the same manner, right? Everything is connected when we think about the pros and cons of different CG locations, right? So stall speed is important, right? Remember that stalling can happen at any single airspeed or any airspeed, right? Every single airspeed, okay? That has nothing to do with it. It's only when we exceed the critical angle of attack when a stall happens. So stall speeds happen at a faster airspeed when we have increased things like load factor and stuff like that, right? So if we have a let's just think about this. If we have a forward CG, right? We know that the arm between the CG and the center of lift has increased, right? Increasing the moment. Okay? So that generates that tail down, or I'm sorry, that generates that nose down force that we've been talking about. And in order for us to keep our nose up, we have to add back pressure, right, to supply that tail down force. Okay? When we add the tail down force, not only does the nose go up, okay, but our angle of attack on the wings also increases. When that increases, right, remember what happens to our airplane, right? We're getting that much closer to that critical angle of attack. So if we're having to hold in back pressure that keeps us close to that critical angle of attack, then we will have higher stall speeds, right? Think about entering a turn at that already kind of high angle of attack. It would be easy to exceed that critical angle of attack because we know we're going to have to add even more back pressure because of load factor during the turn. Okay, so the stall speed goes up anytime we have a forward CG. Cruise speed is the next thing, right? And we can just trace that thought process. So if we know that a forward CG requires more tail down force, that's more back pressure we have to put in, right? Which increases the angle of attack. And when the angle of attack increases, we do generate more lift, but we also generate more drag, right? Induced drag specifically. And induced drag, or any kind of drag, I guess, slows down our airspeed, right? So we don't have as fast a cruise speed. And you can, if you really want to try to increase it, you can add more power, right? But eventually you're going to run out of excess power. You won't have enough to go as fast as you would be able to go with a more aft CG. Okay, and then stall recovery we've already kind of talked about, right? If I have more forward CG, then the tendency of the aircraft is to nose down, right? If I release the controls, the nose will drop down. And that makes stall recovery easier because the only way to break a stall is to go below the critical angle of attack, right? So the airplane essentially does that for you. And if your intention was to stall in the first place, the airplane just makes it hard to do that, right? If you have a forward CG. So stall recovery is good for the forward. And when I said it was a kind of situation, the truth is that the allowable CG limit of the aircraft is calculated so that you still have a forward CG overall. Okay, so within the range, you can have a forward CG and an aft CG, but every single allowable CG location is more of really a forward CG, okay? And the reason for this is so that you have good stall recovery. Cessna knows that people use their airplanes for training a lot. Um, it's a popular airplane, right? And they want people to be safe. So that's how they design the aircraft, is to always have somewhat of a forward CG, even when it's all the way aft to the allowable limits. So just know you will always have that nose down tendency. It might not be as strong if you have an aft CG, but it will be there. All right, a couple more charts here. Shortcuts. So these are some loading charts and things like that. So what the loading chart does is it allows you to figure out the moment for things that are being loaded onto the airplane without having to actually like sit down and multiply. You just find the weight of whatever it is and the appropriate line, and then follow it down to the load moment. So if I've got 250 pounds worth of people in the front, right, then I would find where the line hits that and then go down, and that's about 9,000 pound inches. Okay, so about 9,000 for that. And just keep in mind that everything is divided by 1,000 down here. So just make sure your charts are consistent. Sometimes on test questions, I know they'll have like one divided by 100 and then the other like not divided at all. So you'll have to put the zeros back on to get an accurate figure. But you can see here, both of the bottom axes here between these two different charts are both divided by 1,000, so you don't really need to do anything with that. So once you've found all the moments and everything for your airplane, then what you can do is you can take the weights and the moments and you can again find where they meet here on the center of gravity envelope, and this just saves you the step of not having to divide that moment by the weight to get the arm. You just kind of find where these values meet and then see if you're within or not. And the shape is different for this particular envelope, but these are the same limits as if you use the other chart I showed you. It's just trying to save you a step. Okay, so just be sure that you're not using this one and doing it the other way. They are right next to each other in the POH, and sometimes people get confused on those. All right, last thing is weight shift, right? So this is an important formula to remember if you should find yourself in a scenario where you need to move your CG, right? So if you've loaded up your airplane and let's say everything you have with you just like absolutely has to come with you, right? You can't like take anything out. If the CG is not within limits, but the weight is, you might have to move some things around, right? And then rather than sitting there and doing weight and balance like all over again, you can just use this weight shift formula to move something to reposition your CG. So you can use it for a number of things. You can figure out how far to move something in order to change the CG. You can figure out if I move something this far, how much will that change the CG? You can figure out how much you need to move, right, in order to change the CG. You can do a lot of stuff with this equation. The way that I remember it is this phrase here. It's weird, but it works, I promise. Whoa, TWA, change your CG before I rip both your arms off. That's how I remember that. Okay, so let's just break it down. So the whoa is really like WOO, and that's weight of object shifted, right? So weight of object. Okay, whatever we're moving, that's what that is. And then that is placed above TWA, or total weight of aircraft, on one side of the equation. And then we set that equal to the change in CG, right? So change your CG. And then we put that over the distance between the arms, right? So if I'm moving it from station 73 to station 80, that would be a distance of 7 inches moved, okay? So that's where both your arms comes from. So whoa, TWA, change your CG before I rip both of your arms off, okay? So if we run an example really quickly, let's say our airplane weighs 2,200 pounds. Okay, so that's the information I know so far. Okay, so let's say it weighs 2,200 pounds, which is within the limits, but let's say my CG is too far aft. Let's say my CG is 1.5 inches too far aft. So what that tells me is I need to move something so that my CG can move forward by 1.5 inches. Now, for moving forward, right, then we are technically creating a negative arm, right? Because we're moving it forward, okay? So if I make this negative 1.5, right, we want a CG change of 1.5 inches forward. Then I can plug in the other thing that we have, right? So let's say that I don't know how far to move something, but I have, I don't know, 150 pounds of books that I can move. I don't know how far to move it though. So we can go ahead and we can cross multiply, right? So the information I have here so far is I have 150 pounds of books that I'm moving, so that's the WOA, and then the TWA, which is the total weight of the aircraft, is 2,200 pounds. I set that equal to change in CG, right? I know what the change in CG needs to be. It needs to be negative 1.5, but I don't know how far I need to move the books in order to make that change happen. So that's what the X is. So if we cross multiply with my terrible mouse writing, we get 50x equals negative 3,300 pounds. Okay, so if we divide both sides by 50 to get x by itself, then we end up with, see, that cancels. Let's see here. That's going to be 60 and then 5. So 65. So negative 65. I think my mental math is strong today. Okay, so what I just figured out is that if I want to move my CG forward by 1.5 inches to get within limits again, I need to move my books forward 65 inches. So if there's a station that's at least 65 inches forward for my books, then that will put my CG back in limits. Okay, so that's all I figured out there. So negative means move forward, positive means move back. Okay, that's it. If you feel like it's more confusing to have the negative in here, then just remember which direction you are doing the move in. Okay, you can have it set up to figure out how far to move, or I'm sorry, how far your CG needs to move. So for instance, if the information I have is, let's say my aircraft weight is again 2,200 pounds, and I don't know, for just odd reasons, want to move my, I don't know, move my 30 pounds of uh, bowling balls. Yeah, that's probably a good example. So I want to move my 30 pounds of bowling balls. I want to move them from baggage area 1 to baggage area 2. So that means I'm moving them back. Let me see here. I can figure out how far that move is if I go back to the loading chart. Okay, so I'm moving them from baggage area 1 to baggage area 2. So that's a difference of 28 inches, right? So 123 minus the 95 is 28, right? That's a difference of 28. So if I go all the way back, there we go. So 28, and I'm moving it back. So if I'm moving it further aft, I will keep the number positive. Again, if it throws you, just remember which direction you're moving in. Okay, so I have 2,200 x is equal to, see, mental math is probably not going to save me here. That's 56, and then another 28, 76, 94, 940, I think. I hope. Otherwise, my math is really awful. Is it? I gotta check now. No, I think I did that wrong. I think it's 840. My mental math is not strong today. Let's see, 28 times the 30. Yeah, 840. It's like that doesn't seem right because 30 times 30 should be 800 or 900. Okay, divide both by 2200. This is like scribbling at this point. Okay, this one I'm not even going to try to butcher. I'll just leave the calculator to do this. So the 84 divided by the 220 is 0.38. So 0.38. Okay, so the importance of this answer is if I were to move my bowling balls back there, that's how far aft the CG would move, right? That makes sense that it would move back if I move more objects back. But let's say I was, I don't know, 0.3 from the furthest aft limit for my CG, then this would be a problem, right? Because this would put me outside of that. So that's why I would check that. Okay, but just remember, whoa TWA, change your CG before I rip both your arms off. Okay, that's going to be important on the test and in the future. Okay, so that's really all I have for you guys. Let me know if you have any questions at any point in time, and see you guys later.